Hello, Smart Medicoz. Welcome back to the deep dive. So you've asked us about something really quite impressive that the body does. How do your immune cells, your tiny defenders, actually pinpoint and get to the exact spot they're needed during inflammation? Today, we're going to unpack that incredible journey, really step by step, almost like walking through the key slides.
Yeah, it's fascinating stuff.
Yeah.
The body's ability to deliver these crucial cells, think neutrophils, macrophages, right to the site of trouble, whether that's, bacteria or just damaged tissue. The goal is clear. Defense. They engulf invaders, release signals, all that. But, and this is key, it's a delicate balance. These activated cells, they pack a punch. They can cause collateral damage too. So their movement is very tightly controlled.
Okay, so these cells are just cruising in the bloodstream. It sounds, chaotic. How on earth do they know where to stop? How do they not just zip past the problem?
Right, it definitely seems like they could just fly by. But it's anything but random. It's a really precise sequence. First step, margination. Basically, instead of staying in the central, fast-flowing blood, they move towards the edges, the periphery of the blood vessel, especially where blood flow might slow down a bit near inflammation.
Ah, okay. Like pulling over to the slow lane on the highway?
Exactly like that. A good analogy. That gets them closer to the vessel wall, ready for the next step.
And what is that next step? Getting closer is one thing, but how do they, make contact?
This is where it gets really clever. They start rolling. It's a kind of loose, temporary sticking to the vessel wall. Mm-hmm. It's mediated by molecules called selectins.
Selectins.
Okay, think of them as like little sticky notes. L-selectin on the leukocyte, E or P-selectin popping up in the activated vessel lining. They grab onto specific carbohydrates, slowing the cell down, making it tumble or roll along the surface. It's not a hard stop, just slowing down.
So rolling is like testing the waters before they commit.
Precisely. It allows them to sample the environment, and then if the signals are right, they do commit. That's the next stage. Adhesion.
Adhesion. Okay, so this is the firm grip.
Exactly. Much firmer. This involves another set of molecules, integrins, on the leukocyte surface. Mm-hmm. These integrins usually exist in a kind of low stickiness state.
Right.
But when the cell gets activated, often by chemical signals called chemokines coming from the inflamed tissue, these integrins switch. They flip into a high affinity, high stickiness state.
Ah, like activating superglue.
Sort of. They then bind really tightly to partner molecules on the vessel wall, things like ICAM1, and that anchors the cell, stops it cold.
Okay, stopped. Anchored. But they're still inside the blood vessel. How do they get out into the actual tissue where the problem is? That sounds like a barrier.
It is a barrier. And getting through it is the next critical phase, transmigration, or Diapedesis is the other term. It mostly happens in these small vessels, the postcapillary venules. The leukocytes literally squeeze themselves between the endothelial cells lining the vessel.
Squeeze between them.
Oh.
Yeah.
Yeah, guided by molecules like PCAM1. And once they're through that endothelial layer, it's not over. They then have to get through the basement membrane, that tougher layer underneath. To do that, they sometimes release enzymes like collagenases to basically digest a path through.
They literally chew their way out. Okay, so now they're in the tissue, but inflammation might be spread out. How do they find the absolute ground zero?
Right. Good question. They need navigation.
Yeah.
And they get it through chemotaxis. Think of it as following a chemical scent tray.
Like breadcrumbs.
Exactly like breadcrumbs. Chemoattractants, these could be bits of bacteria or signals our own body makes, like IL-8, C5a, LTB4. These chemicals create a gradient, stronger concentration, closer to the source of the trouble.
I see.
The leukocytes sense this gradient. They have receptors for these chemicals. This activates signaling inside the cell, making them extend little protrusions, kind of like feet called philopodia, and pull themselves along, actively migrating towards the strongest signal, homing in.
It really is like a microscopic military operation, isn't it? With precise timing. Do different cell types arrive at different points?
Oh, absolutely. There's a definite timeline, and it's usually quite predictable. Neutrophils are the first responders, the shock troops, if you like. They dominate the scene in the first, say, 6 to 24 hours. But they're relatively short-lived.
Okay, the quick reaction force.
Right. Then, monocytes arrive a bit later. They mature into macrophages in the tissue. These guys come in typically between 24 to 48 hours. They're longer-lived, can even divide there, and handle more sustained cleanup and repair coordination.
Makes sense. Different roles, different timing.
Exactly. Yeah. Though there are exceptions, of course. Viral infections, you might see more lymphocytes early on. Allergies. Eosinophils might be the main players. It depends on the specific trigger.
So stepping back, understanding all these details, the rolling, sticking, squeezing, chemotaxis, what does it really mean for us, for our health?
Oh, it's hugely significant. I mean, clinically, very relevant. Think about genetic conditions where this process fails. Leukocyte adhesion deficiencies, for example. If these cells can't adhere properly, can't get out of the bloodstream,
They can't fight infections in the tissues.
precisely, leading to recurrent, severe bacterial infections. It highlights how critical every step is. And on the flip side, think about chronic inflammatory diseases, arthritis, IBD, things like that.
Where inflammation is the problem.
Right. In those cases, this whole pathway is often working overtime, causing damage. So many modern therapies actually target parts of this process. Drugs that block integrins, for instance, or block key cytokines like TNF. They aim to reduce leukocyte recruitment, dampen the inflammation.
So we're using this knowledge to develop treatments.
We are. But it also shows that balance again.
Sure.
These drugs can be very effective, but by dampening the immune response, they can also increase the risk of infection. It's always a trade-off.
What an incredible deep dive. It's just amazing. From that initial gentle rolling along the vessel wall to the firm sticking, the squeezing through tiny gaps and chasing those chemical scents, it's clear that getting leukocytes where they need to go is just this essential, highly coordinated, frankly astonishing piece of biological engineering. Selectins, integrins, cytokines, chemokines, so many players.
It truly is. It really underscores the body's incredible capacity for self-defense and regulation. And maybe a final thought for you to consider, looking ahead. Given this delicate balance, fighting infection effectively while trying not to damage our own tissues, how might a deeper, even more granular understanding of these molecular interactions, how might that lead to even smarter, more targeted, perhaps safer therapies for all sorts of inflammatory diseases in the future?
Definitely food for thought. A fascinating microscopic world indeed. Thank you for joining us today as we unpacked leukocyte recruitment. We hope you feel a little more well-informed.